I'm sorry. Okay, so in Google Classroom, under your classwork tab, there's an assignment there. Oh, okay, it's me, I promise. Okay, in Google Classroom, under your classwork tab, there should be an assignment in this week called Global Convection Currents Drawing. Click that button and then open up that PDF. Don't do anything else at this point. We're going to be using a new program today called Cami. Okay, it's an app that works with Google in order to draw on, put pictures into, do cool stuff with PDF documents. What you're going to do here is go to the top of the screen. There's this little open with menu. From that menu, choose Annotate with Cami. Do that now. And once it opens, it's going to ask you to sign in with Google. So go ahead and click Sign In with Google button. I think it's the top one on the page. And the first time you log into this, which is now, it's going to walk you through a couple permissions. It's going to ask you, are you a student? Are you a teacher? Grade level, that kind of stuff. Go ahead and click through that stuff. And then it's going to, you shouldn't be typing anything right now. You just need to click the Sign In with Google button. Just click the Sign In with Google button. And then it's gonna walk you through a few permissions. Just accept those. It's gonna say, do you want to authorize Google Drive? Click yes, I authorize Google Drive. It's gonna ask you to verify your email address, do all those things, and eventually it should pop up to this screen that I have right here.
I don't even have open, like to open with Cami.
At the very top? Oh, pause. All right, so what this is going to be a two-dimensional drawing of the three-dimensional concept that you have been learning about this week, those global convection currents. Up in the top left-hand corner, and you don't need to touch it right now, I'm just going to show you on my screen. Up in the top left-hand corner, I have put a three-dimensional diagram. You probably saw this at some point this week, whether you realize it or not. This is a decent three-dimensional picture of Earth's global convection currents, which is what we're going to be discussing and drawing together. So I just put this up here so you can reference it later if you want to. You won't need to mess with it right now, so just leave it alone. Okay? I've also linked a video of me doing this lesson previously. Again, you don't need to go to that. We're going to do it right now, but that's there in case you need to review it. So the first thing we're going to do is we are going to talk about the equator. What did you say it was like at the equator? It's hot, right? And we said that hot air, because it's less dense, expands, it's got low pressure. So what I want you to do, over on the left, go to the text box function, and I would like you to choose a font size of 18 and choose color red. So over on the very left, the text box, which is the big T, 18 font size, red. To put a text box in, all you got to do is click, and I'm going to click over here near the equator, but off to the side. And in that text box, I'm going to type warm, comma, low pressure. And then you can just click back on the text box button and it'll leave it there for you. You can come back here and move this around if you need to, if you got it off kilter a little bit. So the equator, It's warm because it's always being heated by those direct sunlight. Okay, now, likewise, let's go up to the North Pole and down to the South Pole. But this time, go to your text box, leave it at 18, but choose blue. Just like in art, we're going to associate blue with cool and red with warm. So we're going to go up here, right above where it says 90 degrees north latitude. We're going to make a text box. And we're going to type cold, comma, high pressure, just like we had talked about at the beginning of class. And again, if you get that a little off, you can always come back and move it. Yes, ma'am.
Can I put it under it? Because
Yep, that's fine.
above it keeps coming
That's
down.
fine too, as long as it's up there near it. North Pole's cold, just like we talked about a few minutes ago. They don't get direct sunlight. So it stays cold, and that cold air is more dense, and more dense air pushes on itself more. So it's got high pressure. Yes, sir. It's not. You gotta go to the text button again. Still blue. We need another text box, but here's a trick for you. Instead of going and making another text box and typing the exact same thing in it, here's what I want you to do. Go up to your very top menu where it's got the little mouse button looking thing. It says select. And if you click on that, it pops open three options: select, hand tool, and select annotations. Click the bottom one. Now when you come over here and you hover over your cold high pressure thing, if you can click on that, and it pops open some options. It says copy, paste, or delete. I'm going to copy that, and then I'm going to paste that. And you'll notice that it should put it on the page for you. Then you can go in there and drag it down to where you need it, which is 90 degrees south latitude, because it's also cold, high pressure air there. So instead of having to copy everything again, instead of typing it again, I copied it and pasted it. All right, now click back onto your mouse button up there at the top, and you'll be back to normal. Okay? Now, air always moves from areas of high pressure to areas of low pressure. So what we should expect, now don't draw what I'm going to draw. Don't do anything. Just watch my board. What I should expect is that the air up here at 90 degrees north, because it's colder, high pressure air, it's going to want to come down to the equator. Here's the tricky part. We're drawing a terrible two-dimensional diagram. We got to think about it three-dimensionally. We have to keep in mind that it really looks like this. The stuff we're drawing on here is not just flat, it's got depth. It's three-dimensional. So I like to think of these convection current bands. See these little tubes? They're like donuts wrapping around the Earth. These convection current cells, which you were learning about. So we're going to be drawing those. To think about them though, and again, don't do what I'm doing quite yet, air should move this direction. It should move from 90 degrees north straight to the equator. If I put that a little more three-dimensionally, it might look something like this. These are arrows of air moving from the equator, or from the 90-degree North Pole down to the equator. Does that make sense?
Yeah.
It should be doing that. And it should be going from 90 degrees south to the equator, because high pressure always moves to low pressure. So it should be doing something like this. But it's not. And I'll explain why. I'm going to undo all this. Yes, sir? I'll just leave it there and remind me at the end of the period. Okay? Here's what I want you to do now. Go get yourself this drawing tool. Looks like a little marker or pen or something.
It's a paintbrush.
Click on the paintbrush. There you go. Make it size 2 line, and let's choose the blue color from the menu there.
That's a sick color.
All right, we are going to draw some global convection currents. So we just said air should be moving from 90 degrees north down towards the equator, right? We're going to represent that with a line. Here's the problem. It never makes it to the equator because as it starts to move south, it heats up. It gets hot. And what happens when air heats up? Expands, becomes less dense, and rises. All right, so let's go up to our North Pole. And we're going to start an arrow at 90 degrees north. Now, I know this is kind of tricky with your fingers on the mouse pad. Just do the best you can. I'm not judging you on your art. I just want you to have the experience of using this a little bit, okay? If you have a mouse, great. It'll be a little easier for you, okay? So we're going to take an arrow from 90 degrees north, and we're going to move it kind of along the surface just before 60 degrees north. And we're going to draw a little arrow. This arrow represents a wind that is moving from the North Pole south to 60 degrees north. And at about 60 degrees north, it starts to heat up. And it rises, it expands and rises. So we're going to draw another arrow right next to this one, up and away from the Earth.
Should we take a second just to erase if we need to erase?
Yep, if you need to,
Erase, you go. Yep.
there's an eraser or there's an undo button at the top. Yeah, sometimes it takes a second for the undo button to pop up. It saves your changes and then pops up the undo button. So, again, this is 2 dimensions. We got to think about it. What does air going off the surface of the air look like? Well, if I was looking at a 2-dimensional picture, that's what it looks like. It's just an arrow moving away from the Earth's surface. It's rising off the Earth's surface. Make sense? Air at the North Pole is really cold, right? Air that's cold is more dense. More dense air sinks. So we've got air at the North Pole that is actually sinking. You can draw an arrow like that. Maybe I can zoom in a little bit. There, how's that? So we've got sinking air at the North Pole. It flows south to 60 degrees north. It heats up. It rises off the surface. This rising air is going to replace the sinking air.
But, whoa, he's like 4 arrows. So
Correct.
I only have 3.
And what did we just create? A convection current. Those are those convection currents that we've been learning about for a few weeks now. All right, now let's go down to the South Pole. The South Pole, 90 degrees south, things are going to happen in a very similar way as they did at the North Pole. Air is really cold at the South Pole, and it wants to get to the equator. It wants to travel north to the warmer equator. So let's draw a line from the South Pole towards the equator. But again, at about 60 degrees south, it's going to get warm. And it's going to kind of stop there. And what did we say happens to warm air? Expands and rises. All right, so we're going to draw an arrow off the surface. And again, some of you are probably thinking, well, Mr. Fulton, that arrow is going down. How is it rising? Well, it's not going down. Remember, the Earth is a sphere. It's just going off the surface. That's the important part. Remember, 3 dimensions, 2-dimensional picture. So it's a little harder to visualize. And again, remember, air at 90 degrees south is really cold. It sinks. So draw yourself a sinking arrow.
Hold on. How do you get out of the art mode?
And then air that's rising replaces air that's sinking, and we've got another convection current. The next thing I want you to do is go back to your paintbrush tool, your drawing tool, and change the color to red.
Where's the eraser?
Hey folks, please don't forget I'm trying to record here. with that red paintbrush, we're going to go to the equator. I'm going to zoom out a little bit. Now, the equator, we said it's really, really warm. At 30 degrees north and 30 degrees south, because it's not right next to the equator, it's not as warm. So this not as warm 30-degree air is cooler than the equator air, right? So air always moves from areas of cooler high pressure to warmer low pressure. So air at 30 degrees north is going to start moving toward the equator. So let's draw an arrow toward the equator. And when it gets to the equator, boy, it gets hot in a hurry. And what happens when it gets heated? It expands, becomes less dense, and it rises off the surface. Air at 30 degrees north is pretty cool compared to the other air around it. And cool stuff tends to sink. So at 30 degrees north, we're going to have a sinking arrow. And just like before, the air that was rising cools down in the upper atmosphere and replaces that air that was sinking, and we get a convection current that forms. And the air just keeps getting heated by the Earth, cooled in the upper atmosphere, heated by the Earth, cooled in the upper atmosphere, and we get those convection currents, just like we've been talking about. All right, go to 30 degrees south. And again, air at 30 degrees south is cooler than air at the equator, and it's going to start moving towards the equator. When it gets near the equator, it gets heated, it rises. Air at 30 degrees south is sinking because it's cooler. The rising air replaces the sinking air, and we've got a convection current. Again. Now I want you to go back to your pen tool, your drawing tool, and choose purple. Because red and blue make purple. Okay? Now, in between 30 degrees north and 60 degrees north, something a little different happens. The temperatures between 30 and 60 degrees north aren't that extremely different. So we don't have a temperature-based convection current that forms. It's a little different. See this air sinking at 30 degrees north? It pulls air down to the surface with it. So let's go ahead and draw a purple arrow next to that red arrow.
Hold on, it won't let me go.
And then this goes.
It won't let me go.
Oh no.
And then at 60 degrees north, see the air that's rising off the surface? Well, it's pulling air with it. So go ahead and draw a purple arrow next to that one. This sinking air replaces this rising air, and this rising air replaces this sinking air. And we have another convection current. Now this one's cool. Since it's created by the other convection currents, it works backwards from the other ones. It cycles in a different direction. And we'll talk more about that tomorrow. But let's go down to the southern hemisphere real quick. Air that is sinking pulls air with it. So draw yourself an arrow sinking. Air that's rising at 60 degrees south rises with it. Sinking air replaces rising air. Whoa, that was a weird one. Undo. Sinking air replaces rising air. Rising air replaces sinking air. And we've got another convection current. So here's our picture so far. What we've drawn is exactly what's in this 3D image up here. See how they've got their convection currents in like those little three-dimensional tubes? That's what we're drawing, just on a two-dimensional scale. All right, last step here. Go up to this Turn In Save button, click it, and then scroll down to Save Now. Just to make sure that all of our changes are saved. That way, when you come back in tomorrow, it'll open up and it should have all of the things we've put on it still there. There's no need to turn this in or anything right now. We're going to work on it some more tomorrow. All right, great. So don't draw what I'm drawing quite yet. I'm just going to show you something. Air at the North Pole should be moving north to south, correct? And air at the South Pole should be moving from the south towards the equator. Make sense? And that's exactly what it does. However, if you remember back to our discussion about the Coriolis effect, the air doesn't move in a straight line like it's supposed to. In the southern hemisphere, it turns to the left, and in the northern hemisphere, it turns to the right. So let's undo those arrows. Let's go to the southern hemisphere first. So here's where you can start drawing. Get your drawing tool. Let's choose black, size 2. And let's draw an arrow. But instead of drawing it from the South Pole north, it's going to turn to its left. And I'm just going to draw a couple arrows like that. So these winds don't flow south to north. They actually flow east to west because the Coriolis effect turns them. And the same thing is going to happen at the North Pole. This one's a little trickier to look at because you have to put yourself in the arrow's point of view. So this thing's actually going to start in the north and try to travel south, but it's actually going to end up turning like this, to its right. I don't like where I put those. I'm going to undo them and start over. There we go. Just space them out a little bit better. And you'll notice that the north polar region looks really similar to the south polar region. The arrows are both moving from the east to the west. Now, the arrows in the north, they are turning to their right. But Mr. Fulton, it looks like they're going to the left. I know, from our perspective. Put yourself in the arrow's perspective. In other words, look upside down. Those arrows in the direction that they're moving are turning to their right. Does that make sense? You can do what some of you are doing. You just turn your screen upside down. Look, they're turning to their right. And if you turn it back upright, the southern hemispheres are turning to their left. But because they're in different hemispheres, they're both moving east to west. All right, let's name them. So let's get a text box. Let's make it 24 size and green. And then we're going to go over here to the right-hand side where we just drew those arrows. We'll make a text box, and we're going to call these things the polar easterlies. And I'll put this bigger so you can read it. Polar easterlies. So remember, we always name winds by where they come from. These are coming from the pole, so polar, and they're coming from the east, easterlies. So we would call this an easterly wind, polar easterlies. I need to type that again, but I'm going to save myself a little time of typing. So if I go over to the select tool at the very top and go to the select annotations, it's the one that looks like a square. If I click on the text box that I just made, a box will pop up that says copy, paste, and delete. I'm going to click copy, then I'm going to hit paste, and it should put a new copy in there for me. You might have to click allow on your screen for the paste function to work. And then I can just drag this down to the southern hemisphere to label the other ones. Because remember, whatever happens in the north happens in the south. Whoops. There we go. How do I get that unhighlighted? Somehow I highlighted everything. There we go. So we've got a band of wind in the north and the south called the polar easterlies. And again, it's this big convection current that forms. If you remember back to some of the videos you've been watching, we talked about the cells yesterday, how they called these wind bands these cells. That's the name of the convection currents. This is called the polar cell. You don't need to know that. But the polar cell at the surface of the Earth, where we feel the wind, is called the polar easterlies. That's the wind, the band of wind. It's called the global wind belt. All right, let's go to the equator region. And I'm going to draw some lines that I don't want you to follow quite yet. At the equator, if you look at these arrows over here, we've got a wind going from the south to the equator and from the north to the equator. So if I was standing there, what I should experience is this, a wind moving from the south to the north. But we know that doesn't work that way, right?
No.
What happens to it? It turns to the left in the southern hemisphere. So let's undo this. And then I'm going to draw an arrow kind of like that. We'll do it a couple more times.
Can you do this?
Yep, you can do this now.
What color?
I'm just using black for all my arrows inside there. So these are another east wind. Something really similar happens in the northern hemisphere. In the northern hemisphere, air should be moving from the north to the south. Don't draw that one yet. But it turns to its right. All right, and again, here's one of those situations we're going to have to put ourselves in the perspective of that wind. So it's actually going to do this.
You can draw this now?
Yep, you can draw these. And you'll notice it mirrors what we just drew in the southern hemisphere. So these are also an easterly wind.
How do you do this so neatly?
I have a mouse.
So do I, see?
All right, so let's go get a text box. We'll leave it 24. We'll leave it green. And let's name these. These have a special name. Does anybody remember this name? Of this wind band? Anyone remember it?
The Georgians. The Northern Trade Winds.
Trade winds. These are the, whoops, no Q. These are called the trade winds. And you can copy that, or what I think is easier in this situation, because the words are pretty easy, just make another text box and put it down there. Probably faster than all those clicks. So both of those bands of wind, these global wind belts, are both called the trade winds. Now the reason they call them the trade winds, and I can't move too far because I'm hooked to a cord here, but I'll show you on my globe. The reason they call those the trade winds is because they were used in trade. So when the European superpowers here, when they wanted to start spreading out, exploring, they used these trade winds to trade with other places in the Western Hemisphere. Now, this turned into spice trade and sugar trade, and unfortunately, at some point, it turned into slave trade. Have you heard of the trade triangle before? I think you learned about it like in 5th grade, maybe. So they would come from Europe, and they would kind of navigate down the coast of Africa, and they would use this trade wind belt. I don't know if you can see that very well on my globe, but they would use this trade wind belt to go from Africa, basically, over to the Americas. And then they would navigate kind of along the coast of the Americas. They were sailing ships, so they had to have some kind of wind that would help push their sails. Well, these trade winds were moving in the direction they wanted to go. So they ended up naming this wind belt the trade winds because of all the trade that occurred from them. Okay? All right, in the middle. Let's get our drawing tool. Now, according to our arrows that we've drawn here, this one's moving from the south towards the north. But it's not going to do that, is it? It's going to curve to the In the northern hemisphere, it turns to the right.
Right.
So instead of drawing an arrow straight up, I'm going to draw an arrow like that. Go ahead and put those in. And those are pretty easy to understand because we're looking at their direction already. Obviously, those arrows are going to the right. In the southern hemisphere, it's going to do the same thing. They're going to turn to their right, but they're moving south now. So their right, instead of going straight down, I'm sorry, they're going to turn to their left, my apologies. They're going to do this. And again, if you want to put yourself in their perspective, just kind of flip your screen upside down for a second, and you'll see that they are in fact turning to their left. Now, because of the Coriolis effect, these winds are not moving north and south now. Now they're moving west to east. Let's get our text box back. We'll make it green again. And we'll type in here, these are called the Prevailing Westerlies. And I'll zoom in so you can see the spelling. How's that?
Good.
Prevailing Westerlies. So again, we always name winds by where they come from. We call these westerly winds because they're coming from the west. Prevailing is a word that just means to take over. So in this region of the globe, it's the westerly wind that's taking over. This is the wind belt that those traders we were talking about would use to get back home to Europe. So if you want to look at the globe, here we are. We're in the United States, or Central America, maybe somewhere. It wasn't the United States at the time. But to get back to Europe, I can't use the trade winds. They're going the wrong direction. So we would use these prevailing westerly winds, and it would take them back into Europe. And this is where we got this trade triangle. Boom, boom, boom. 3 points of the triangle there. So Europe, Africa, United States. This became a really popular trade route, mainly because it was the winds they were able to use to get them to those places. Oh yeah, we're going to do that. Absolutely. So this name in the northern hemisphere is the exact same as it is in the southern hemisphere. So I'm going to use the copy feature. So I'm going to go to select Annotations, click on it, copy, paste, and then I'll just drag that down to the southern hemisphere, named exactly the same. And this is the really great part about this, is if you can learn what's in the northern hemisphere, everything is just flip-flopped, mirrored to the southern hemisphere.
Wait, I clicked on the wrong one.
Prevailing Westerlies. All right. Questions so far? Yes, sir.
My computer's almost dead.
Yeah, plug it in. You can work back at the workbench maybe. All right, a few more things and then we're almost done here. Next thing I'm going to do is go grab another text box, but now I'm going to change the color here. I'm going to use just gray, like a dark gray color. You can use black or whatever you want. I would recommend not using one of the colors we've used so far. Now at the equator, 0 degrees at the equator, we've got air. According to our arrows here on the left, we've got air rushing towards the equator from the north and air rushing towards the equator from the south. But when it gets there, it gets hot. Air that is heated expands, becomes less dense, and rises, right? So if I'm standing near the equator, I've got air coming at me from the north, air coming at me from the south. But as it gets to me, it heats up and rises. And then it cycles away from me. Then it comes back towards me, rises, cycles away. So if I'm actually standing at the equator, this wind never really crosses my face because of the way the convection currents work. So at the equator, it's actually a relatively calm area. Weather patterns don't really cross over the equator. They can't because of the way the Coriolis effect takes them kind of away from the equator. All right, so this calm area, I'm going to put a text box right here along the equator, and we're going to call it the DOLDRUMS, the doldrums. And you probably encountered that word a couple of times during your stations. I'll zoom in so you can see the spelling. DOLDRUMS, doldrums. It's just a word that means kind of calm, still. And again, it's calm because, well, nothing really crosses over. So when you talk about hurricanes, we'll talk about hurricanes coming up. Hurricanes in the northern hemisphere never cross into the southern hemisphere, and vice versa. They can't because of the way the convection currents are moving. Speaking of areas that are relatively calm, 30 degrees north. Remember those trading ships we were talking about with the sails? You need wind for sailboats to work, right?
Yep.
Well, at 30 degrees north, you can see air is moving away on both sides, right? And it's sinking there. And then it moves away. And then it rises and it sinks back down near 30 degrees north. And then it moves away. So here's another place of the globe where air doesn't really cross over very much. There's not a lot of movement between the two zones. So it's very calm again. And the legend, as it goes, I guess, is these sailing ships that were in that doing those the trading, they would get stuck. Because if you're using the trade winds to go this way, and then you've got to get back into the prevailing winds to go back, well, you've got to cross over that 30-degree line where it's calm. And if it's calm, well, my sailboat doesn't work anymore. So people would get stuck here, I guess, for weeks or months on end as they were on their voyage, and they would run out of food for their horses that they had on the board, and they would just like throw them overboard or something when they died, the horses,
Oh, pleasant.
I guess. That's the way it goes. So they ended up naming these things. Here's a text box. Horse latitudes. They call them the horse latitudes. And they'll do the exact same thing in the southern hemisphere. So I'm going to go ahead and make a copy of that real quick. Copy, paste. I didn't say it was a pleasant story. I just said that was a story. And this is also happening at 30 degrees south. Call it the horse latitudes. The next thing I would like you to do,
Wait, where does the other horse go?
at 30 degrees south,
Oh boy. I'm ready.
I like Albert Einstein's ideas.
right? Next thing I would like you to do, go grab your drawing tool again, but this time we're going to make it size 8. We want a really thick line. And we're going to make it orange. And then right along this 60-degree north line, I'm going to draw kind of a wavy, meandering path. Just something like that. Doesn't have to be exactly like mine. Just make it a little wavy. 60 degrees north, size 8. And then I'm going to do the same thing at 60 degrees south. Just kind of a meandering, gentle, zigzaggy kind of line. Something like that. And then I'm going to go back to my brush tool. And I'm going to change it back to 2. Make it black again. And then I'm going to draw a couple arrows that show the direction that this air is moving. They both move the same way, from the west to the east. So just a couple arrows to show the flow. And I'll explain what this is here in a minute, and we'll name it. Mm-hmm. No, for students who are absent. The kids online aren't doing this. They're not doing this drawing. They're doing Ingenuity. Sorry.
Oh no, I'm saying I'd rather do this.
Oh, yeah,
They'd rather.
I get it. All right, so this area is really cool, literally and figuratively. This polar easterly wind, it's really cold from the North Pole. This prevailing westerly wind, it's not nearly as cold. So we've got high pressure air moving this direction, and we've got low pressure air moving this direction. And remember that whole thing we talked about where high pressure air always wants to be where the low pressure air is? Well, we got a problem because this air wants to be here. Sort of, but not really. So what happens is this polar easterly air that's moving from the east to the west, it wants to turn around and catch up with this prevailing westerly wind. So basically this stuff is moving, and it right along this line that we drew, this wavy line, it does a U-turn. It turns around and it tries to catch up with the wind that's blowing the opposite direction. Well, if you're trying to catch up with something that's moving the other direction, you're going to have to go pretty fast. So this band of orange wind that we drew is really, really fast, talking up to 200 miles an hour wind. Now this is happening way up in the atmosphere, so we don't feel it at the surface, but this band of wind pushes our weather systems and influences where our air comes from, which changes what our weather is like from day to day. This thing is called, and I'm going to get another text box that's gray, and I'm going to label this thing as the jet stream. And if you remember back, you watched a video about the jet stream, that little kind of colorful video. Same thing in the south. It's called the jet stream. Now there are other locations on the map that are considered jet streams. We're not going to label them because they're not as important as this one. But the south gets the same name. And our drawing is complete at this point. We're going to talk a little bit more about it, but it is complete for now. Now, this document, if you ever need to come back to it, you can get to it through Google Classroom. That's fine, but it also lives in your Google Drive. Let me show you what I mean. If you go to Google Drive, and you don't have to do this, just watch where I'm going. In Google Drive, if you didn't know it, you have a classroom folder from Google Classroom that's automatically made for you. And it stores all of the things from your classes. So if I go to 5th period science, there is the paper I was just working on. Cami saved it as I was working, and we just clicked save a final time. There's the picture I drew in Cami. So if I ever need to come back and reference this paper, it's going to exist in my Google Classroom in Drive, the folder that's in there. Okay? This is a time lapse of some weather patterns. It's an animation, actually. Brooke, would you turn the top light switch off for me, please?
Top one?
Yeah. Thank you. So this is a time lapse of weather patterns, animated weather patterns. So they've taken data from, I think 2013 weather data, and they've kind of compiled it into this animation just to give you a sense of what you're looking at. Now, if you follow my mouse, that line that I'm tracing right now is approximately where the equator is. What do you notice?
Air to the right and the left.
Oh, the wind is making a U-turn.
There's a lot of clouds, first of all, right? And what Caleb said, if you look at the direction the air is moving, it's moving from the east to the west. Look at it. Watch it it's moving slowly, but watch the direction. It's moving from the east to the west. That makes sense. That's the trade winds. If we go up here into the United States area, watch the direction of the clouds. From the west to the east. From the west to the east. And same thing if I go down here into South America, like southern South America, cloud movements from the west to the east. Follow them. Which makes sense because those bands are the prevailing westerlies. Now it's kind of hard to see the polar easterlies because there's not a lot of cloud cover up here. But do you notice how the prevailing westerly winds are kind of, as they move up to the top, they're kind of swirling back around? See how they make little swirls? That's because that's where that jet stream is. So we've got prevailing westerlies moving one way, but the polar easterlies moving a different direction, and that pushes the cloud cover, kind of swirls it. And it's moving from the east to the west up there and down here. And again, it's kind of hard to see in this diagram, but that's where that is. All right, let's look at the equator again. Lots of cloud cover, right? What do clouds end up bringing? Rain. So as the air at the equator rises into the upper atmosphere, it's cold up there. So it cools, condenses, forms clouds, and eventually precipitation. Look at the land around the equator. What's here? Amazon rainforest, right? Biggest rainforest in the world. Hey, that makes sense. They get a lot of rain. What's in the middle of the African continent? Rainforest. What's on these islands here at the equator? Rainforest. That makes sense. So these wind patterns are influencing the climate in these areas. All of our big rainforest regions are right along that equator. All right, now look, follow my mouse now. Boom, 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 boom. Yeah, right at that U-turn, right? Which is the boundary line of 30 degrees. What's along 30 degrees? Desert, desert, desert. Look at the northern hemisphere, 30 degrees. Desert, desert. 30 degrees north and south. We've got air sinking. Cold, dense, high pressure air sinking. If we got air that's high pressure that's sinking, there's no room between those air molecules to hold water vapor. So as it sinks to the ground, it's dry, which is one of the reasons, we'll talk about more reasons why those deserts are where they are, but that's one of the reasons why we have these deserts that form along these 30-degree lines, because the air is very dry.